I'll share the lecture notes at the end of the lecture today. I have to share from lecture 11, right? Okay. I had defined the field of fractions. Actually, I had defined the set of equivalence classes denoted by fractions, constructed using an integral domain D. Yes, yes. So a ring is the most basic structure that we have. Then an integral domain has an additional property. It's a ring with an extra property that the product of two non-zero numbers is also non is always non-zero. Then a field is an integral domain with an extra property that all non-zero elements have inverses. So a ring is a particular structure. All integral domains is a subset of the set of all rings, and then all fields are a subset of set of all integral domains. Just to recall what the set was, we had D was an integral domain, and we defined a relation on the set D cross D, excluding the ordered pair 0, 0. D cross D is the Cartesian product of D with itself. That is, it is all the set of all ordered pairs where the first element and the second element are both from the integral domain D. Then we define the relation to be an ordered pair AB is related to ordered pair CD if and only if the product A into D is equal to the product B into C. And such a product will be defined because D is a ring. So there is a multiplication operation. Now we showed that this is a equivalence relation, and we know that every equivalence relation has equivalence classes. So equivalence classes are um, the equivalence class of one element would be the set of all elements in the ring related to that element. And these equivalence classes form a partition of the set. Now we denoted an equivalence class containing an element a comma b by a by b. So by a, uh, when we write a by b, we actually mean the equivalence class containing the element a comma b. Of course, that equivalence class can contain other elements c comma d, e comma f, whatever it is. But then if they are in the same equivalence class, then they are related to each other. So a by ad will be equal to, if AB and CD are in the same equivalence class, then AD will be equal to BC. So as equivalence classes, if I write A by B is equal to C by D, then what I actually mean is that um, A comma B is related to C comma D, which means that AD is equal to BC. Then on that we defined the addition operation as A by B plus C by D is equal to AD plus BC by BD. Then we define the multiplication operation by A by B into C by D is equal to AC by BD. And the ring we considered was the set of all equivalence classes A by B, where A and B are elements of the ring and B is not zero. We showed that this addition and multiplication were two well-defined operations. And then okay, well-defined operation should give you only one output uh, when you give in two input variables. And the output should not depend on the form of the two input variables. So when we so this only arises because there are multiple ways to write an equivalence class. See, when you're adding integers 1 plus 2, there is only one way to write the integer 1 and one way to write the integer 2, mathematically speaking. And then 1 plus 2 is 3. There is no problem there. But when we are doing mod 3 arithmetic, say, then when you're adding two equivalence classes, you can represent the equivalence class in multiple ways. And all those representations will mean the same equivalence class. So the equivalence class containing 1 is the same as the equivalence class containing 4, which is the same as the equivalence class containing 7. So when you add the into equivalence class containing 1 with the equivalence class containing 2, your result should simply be the equivalence class that contains 3, which is simply the equivalence class containing 0. And it should not, the sum should not depend on how you represent the equivalence class. So whether you add 1 bar plus 2 bar or you add 4 bar plus 5 bar, the end result should still be the same. Similar to in how functions, you can't define a function on rational numbers that says f of a by b is equal to e power a plus b. If you define it that way, then f of half would be e power e cube, but then in real number system, half would be the same as 2/4. But if you write half as 2 by 4 instead, even though you mean the same number, f of 2 by 4 will be e power 6. So the same number is giving you different outputs. That shouldn't happen. Well defined would mean that regardless of what representation you use denote an element, the output must be the same. Then we show after that actually I had to show that um, A by B is equal to AC by BC, and for us A by B is equal to C by D if AD equals BC. To show that A by B is equal to AC by BC, we have to show that A into BC is equal to AC into B, which is true because of commutativity. ABC is equal to ABC. It is true all the time. So if you have something of the form AC by BC, that will be the same as A by B. And also A plus D by B is equal to A by B plus D by B would be AB plus DB by B square. This is true because a plus d into b square is ab square plus db square, and ab plus db into b is also ab square plus db square. So the rules of these common rules that we see in integers, they hold for this fraction set also. So these rules that hold for rational numbers, instead of rational numbers, if you replace, instead of rational numbers which are written as a fraction of integers, if you replace that by the frac b, the fraction set, where integers are replaced by elements from an arbitrary integral domain, then these rules still hold. So with that, we said let D be an integral domain, then this frac D, this set frac D is a field. Also, if you consider the elements in D, if you consider to be equivalent to, let's say you have an element A in D, you say that is equivalent to A by 1 in frac of D. Then in that sense, D is contained in frac of D. For example, if you have Z integers, then they are contained in the set of rational numbers because you can write integer 2 as 2 divided by 1, where 1 is the identity element in Z. So we had to prove this now. We haven't proved it yet. So we won't prove, let me copy this here. So we won't prove commutativity. Uh, it is easy to verify that plus and into are commutative in frac D. That's we also call this K. I will call it K from now. So we won't prove commutativity. That follows directly from the commutativity of the addition and multiplication operations in the integral domain D. Then from the definition, we already know that uh, they are closed, addition and multiplication. And what else is left to show that it is a field? I have to show the identity elements, but that is simple. 0 by 1, which is also equal to 0 by a for any element a. Why is this? This is because 0 times a is equal to 0 times 1 is equal to 0. So 0 by 1 is equal to the equivalence. This is actually the equivalence class. These two are equal because 0 comma 1 and 0 comma a are related. That's what it means. And these two are related because 0 into a is equal to 0 into 1 is equal to 0. But we'll simplify the notation and simply write that the fractions are equal. Now this is the identity because if you take some element c by d and add 0 by 1 to it, you get c into 1 plus d into 0 divided by d into 1. This is c into 1 plus 0 by d into 1, which is c by d. So this is the additive identity. The equivalence class of 0 by 1. Similarly, the equivalence class of 1 by 1 can also be written as a by a. It will contain all elements from a by a because a into 1 is equal to a into 1. That's just obvious. So this will be the multiplicative identity because c by d into 1 by 1 is by definition c into 1 by d into 1, which is simply c by d. Again, it is so if a by b belongs to k, then a by b plus minus a by b is by definition ab plus minus a into b by b square, which is ab minus ab plus minus ab by b square, which is 0 by b square, is equal to 0 by 1. So minus a by b is the additive inverse of a by b. Then we have associativity. For addition, it is we have to show that a by b plus c by d plus e by f is equal to ad plus cb by bd plus e by f is equal to adf plus cbf plus ebd divided by bdf. And a by b plus c by d plus e by f is equal to a by b plus ACF plus CD by DF is equal to ADF plus BCF, which can also be written as CBF, plus BED, which can also be written as EBD by BDF. These two are equal, so addition is associative. Similarly, AB into C by D into EF is equal to AC by BD into E by F, which is equal to ACE by BDF. On the other hand, A by B into C by D into E by F is equal to A by B into CE by DF is equal to ACE by BDF. So both addition and multiplication are associative. Then distributivity will only show one side of the distributivity, one distributive law. The other distributive law follows because of commutativity. So if you have A by B plus C by D into E by F, this will be equal to AD plus BC by BD into E by F. This will be equal to ADE plus BCE divided by BDF. On the other hand, A by B into E by F plus C by D into E by F is equal to AE by BF plus CE by DF, which is equal to ADF plus BCEF divided by BDF square. Can also be written using distributive law within the integral domain as ADE plus BCE into F by BDF into F. But we already proved that this is the same as ADE plus. We already showed that you can do cancellation. So here this equality, since these are not numbers but actually elements from the integral domain and these are actually equivalence classes, um, you can't directly write it. You should have initially showed that this is true. That is AC by BC is equal to A by B. That's why we showed it in the earlier lemma. So we have shown all the properties. For a general integral domain, uh, we can construct a fraction set like this. Only thing left is um, multiplicative inverse. So multiplicative inverse is what? For A by B, what is the multiplicative universe? Yes. A by B into B by A will be equal to A into B by B into A, but is equal to AB by AB because multiplication is commutative. But we also know that this is equal to 1 by 1, which is the multiplicative identity. Also, we had excluded the possibility that the denominator is 0 and the numerator is 0. So we only need the multiplicative inverse of non-zero elements, and the 0 by 0 does not belong to this set in the first place. No element has 0 in the denominator, and no element has 0 in the numerator except for the 0 element. So for all non-zero elements, both A and B are non-zero. Therefore, B by A is a valid equivalence class that belongs to the set K, and it is also the multiplicative inverse of A by B. Next, we have to show that the second part, uh, we showed that this is a field, but we also have to show that we can identify D with elements of the form A by 1, and that D is contained in frac D. So this is only up to an isomorphism. Well, I don't think I need to show it as such, because 1 is an element of D. For any element A in D, A by 1 will also be will be an element of K. Yes, yes. So if A by 1 is equal to B by 1, that's only possible if A into 1 is equal to B into 1. That is A is equal to B. So it is a bijective mapping. So it's not exactly contained, it's not exactly an element in the sense that, see, the elements of D are not equivalence classes, right? But the elements of K are actually equivalence classes. So it's not correct to say that the elements of D are actually a subset of K. We can only uh, find a subset of K such that it is isomorphic to D. In that sense, D is contained in K. It is not very apparent when you look at integers and rational numbers, because we have used it over and over again. We simply feel that 2 and 2 by 1 are the same thing. But here in this framework, 2 by 1 is really the equivalence class containing 2 comma 1. So 4 by 2, 2 by 1, 6 by 3 are all the same thing. They're all contained in the same equivalence class. Whereas 2 is simply one integer. It's not an equivalence class. Nevertheless, you can associate 2 with the equivalence class 2 by 1. Then, in that sense, all the integers are contained within the set of rational numbers. So, this set frac D is called the field of fractions. Given any integral domain, you can form a field in this way. Then, as a corollary, you can also corollary is let F be a field. So you start out with a field, not an integral domain. Then let D be a subring. So D is a subring, not necessarily a field. Then since it is a field, F is a field, so it is also an integral domain because every field is an integral domain. And that means that every subset subring of the field is also an integral domain. So D would be an integral domain. For any subring of a field, it would actually be an integral domain. So you can construct the fraction field of D. Then this frac D would be a subfield of F. So there is an up to an isomorphism again. And the isomorphism is using the identification A by B is equal to AB inverse. Actually, the isomorphism is P of A by B is equal to AB inverse. Is the meaning of this corollary clear? Suppose you start out with um, the field of real numbers. Then you consider a subring of that field, which is actually a ring. I mean, you can consider a subfield also, but suppose you have a pure ring, not a field, which is a subring of this field. So here Z is a subring of the real numbers, right? Set of real numbers is a field. Set of integers is a ring, which is within the set of real numbers. Then you can construct this field frac D, right? But for integers, what is frac D? That is set of fractions taking integers. Oh, what is frac of Z? What is frac of D for integral domain D? Yes, what are the field elements? What is this field? Yes, fractions we for integral domain D we form the fraction by writing A by B are the field elements, where A and B are both elements from the integral domain, and B is not zero. But if that integral domain is the set of integers, what is the fraction field then? No, set of all A by B such that B is not equal to zero. What is called when A and B are in integers? No, why? No, Z and frac Z are two different sets. Frac Z contains Z, but frac Z is not the same as Z. Frac Z is the set of rational numbers Q, but not all rationals are integers, right? So Z is contained in frac Z. Frac Z is the set of rational numbers. So this frac Z will be Q, but then this is a subfield of R, right? Q is a subfield of R, where you can write a number half in the field Q. That would be the same as the number 1 into 2 inverse in the field R. Is it is it 2 inverse by itself has no meaning in Z. So in Q you can't really write 1 into 2 inverse. Um, I mean you can write it within Q, but 2 inverse does not exist in Z. Okay, this problem only happens because this 2 inverse has a meaning in Q, but it does not have any meaning in Z. Now is this clear now? Which one? Not P. There's a phi. The isomorphism. See, the problem here is in Q, this division makes makes sense because 1 by 2, you understand what 1 by 2 is, and you understand what 2 inverse is. That all makes sense when you're dealing with integers, but none of it actually makes sense when you move to a arbitrary ring. So if someone says you have a ring, then a ring has only into and plus. There is no notion of division there. This is trying to give a notion of division, but not exactly. This is trying to give a notion of fraction. When you When you write 1 by 2 here, it also kind of carries the notion that you are dividing 1 by 2, right? It's 1 divided by 2 is 1 by 2. But such a kind of meaning doesn't exist for an arbitrary integral domain. And a by b doesn't mean that you are dividing a by b. This doesn't hold. Yes, there's no division in a ring. At least it's not. At least the ring doesn't come with a division operation. Especially some type of ring like the integer and reals and all, reals and rational numbers, you can define a division. But in general, it doesn't come with the division operation. So a by b doesn't mean you are dividing a by b. Simply means the equivalence class containing a comma b. So here this should make more sense if I say instead of everywhere the confusion arises because I'm writing a by b, but actually it makes more sense if I write. So here this is the equivalence class containing the element a comma b. Here it is a into b inverse in the field f. So a and b are field elements. We started out with the field. Then we took a subring of the field. Since it is a subring, they are also elements of the field only, right? So they are also this is contained within the field. So in the field, this B will have an inverse. So this AB inverse is the element of the field. The equivalence class of A comma B is the element of frac D, which you construct using D. This is because uh, if A comma B belongs to frac D, then we know that A and B are elements of D and B is not a zero element. Since B is not a zero element, B inverse belongs to F. By closure, AB inverse belongs to F. So if you identify the equivalence class containing A comma B by the element AB inverse, then this frac D will be a subset of F. Then suppose you do addition in, suppose you do A by B plus C by D. This is actually in frac D. This would be what? AB inverse plus CD inverse. You took this equivalence, if you took that equality. So this would be AD D inverse B inverse plus C into B inverse D inverse. Should be AD into B inverse D inverse plus BC into B inverse D inverse. Should be AD plus BC into B inverse D inverse. Now the result of A by B plus C by D in frac D would be AD plus BC by BD. And if you took this equality, if you took that identification, so what I'm saying is this is phi of A by B plus phi of C by D is this. Whereas phi of AD plus BC by BD is AD plus BC into BD whole inverse is B inverse D inverse B inverse, but commutatively holds. So BD whole inverse is simply B inverse D inverse. So phi of A by B plus C by D, which is this, is equal to phi of A by B plus phi of C by D. I'll instead of this identification, I'll write it is an isomorphism. Yeah, I'll change. No, isomorphism from frac D to a subset of F, a subfield of F. So, see, if you have an integral domain, you can always construct a fraction field, frac D. That I have already shown. And I also said that there is an isomorphism between that integral domain and a subset of frac D. So, in the integral domain, if you have an element A, that you can map to A by 1 in frac D. So, this is actually an isomorphism. So that un under that isomorphism, D is actually within is a subset of frac D. You can view D as being a subset of frac D under that isomorphism. But actually, D is not a subset of frac D, right? Frac D is a set of fractions, which are actually set of equivalence classes. Whereas D is a set of elements. That part you understood, right? Did you understand the difference between D and frac D? That did you understand that D is not actually a subset of frac D? Is that clear to you? You understand that even though I say it is, see what is a subring? It is subring is subset of elements that also form a ring, right? But D is not a subset of frac D at all, right? Did you did you get that? That is very confusing because the example that we have is Z and Q, and we have been brainwashed into considering the two to be the same thing. So in integers, 2 and 2 by 1 are the same thing. That's okay for integers, but that's not okay for a ring, right? Yes, yes. Uh, for example, we are only considering commutative rings. Let's say for just for the sake of example, we did not take into consideration commutativity. Then a matrix ring would also be a ring. Then is there any meaning in writing ABCD divided by EFGH? That doesn't really mean anything, right? So in that sense, uh, or if you wrote, so this frac D is, it's something like this. Okay, I have a better example. So we have matrices. A matrix is a set of elements A, B, C, D. Let's say we have a 2 by 2 matrix, where each of these elements is an integer, right? Okay, let's say we take integer matrices. This is a 2 by 2 matrix. Then what would be a 1 by 1 matrix? No, if no, this is a 1 by 1 matrix, right? Let's say this was integers, right? Is this the same as the set of integers? The set of all 1 by 1 matrices. But what is the difference? You put a bracket around the number, that's all. Other than that, what is the difference? One by one case, there is no virtually no difference, right? So there is almost no difference other than the fact that you have put a bracket like this. You can say this, you can identify, can interchange, you interchangeably use these two things to mean the same thing, but not necessarily, right? One of them is a matrix, another is simply a scalar. But you could say, in a sense, this for each integer you can have one by one matrix containing that integer. That sense, you could say the scalars are all contained in the set of square matrices, right? So you have the set of all square matrices, but whenever you are working in that domain, but suppose you wanted to deal with integers also. Instead of dealing with integers, you could simply say they're the same as set of all one by one matrices. They're included within that. Then whenever you want to add two integers a plus b, instead of adding the integers as integers, you could add them as matrices and you would still get the same thing. No? That's literally no difference, the one by n case. Similarly, if you wanted to multiply two integers, you could simply multiply the matrices, scalar matrices containing those two integers, and the result would be the same. So even though they're two different structures, you have an isomorphism. where an integer is mapped to this one by one matrix containing that integer. When you want to add two integers a plus b, you can simply add the two matrices, one by one matrices, a plus b. This would be equal to a plus b. So this a plus b would be mapped to it. And when you want to multiply two integers, you could actually multiply the two matrices. It would give you ab, right? So in some sense, this set of integers is contained within the set of square matrices. So the same thing is happening here. Initially, you only had elements A, B, C, D, etc. Also, you had one. Then you considered, instead of putting a bracket and listing numbers, or instead of listing ordered pairs C, comma D, E, comma F, you simply wrote A by B. And this A by B is not really a part of this set. It doesn't belong here. But you could, in some way, say that, and each element here does not really belong to the set of all A by B. But you could say, in some sense, this set is a subset of this set by picking B is equal to 1. Could say A is the same as A by 1 for all intents and purposes, even though they are not actually the same. Yeah, so they are structurally equivalent and they are equivalent operationally also. That is, when you are adding and when you are multiplying, if you add A plus B or if you add A by 1 plus B by 1. At the end of the day, you get, if you add A by 1 plus B by 1, you get AB by 1, which you can reverse map to AB. So every element A is mapped to A by 1. Similarly, A by 1 is mapped to A. So instead of adding A plus B, you can do A by 1 plus B by 1. We will get A plus B by 1, which you can reverse map to A plus B. Similarly, instead of multiplying A into B, you can multiply A by 1 into B by 1, which will give you AB by 1. And you can reverse map it to AB. So operationally, they are the same element. The same thing happens here also. You now what you do is you already have a field. You identify a subring within that field. Then you construct a field of fractions from that subring. You don't now you actually don't really get a completely new field. Right. This frac D that I have, it has nothing to do with F, right? The way I constructed frac D. But even though the way I constructed it had nothing to do with F, it ends up such that there is an isomorphism between frac D and F. So what you constructed this frac D using this subring was simply actually a subfield of F already. There was some subfield of F that contained D. You only got it through some other construction. And this is an isomorphism because we showed the addition part. Multiplication, you would have P of A by B into P of C by D is AB inverse into CD inverse, which is AC into B inverse D inverse. Whereas P of A by B into C by D is P of AC by BD is P of it is AC into BD inverse, which due to commutativity this is equal to B inverse D inverse. If it is not commutative, it would have been D inverse B inverse, but because of commutativity, it's just B inverse B inverse. So phi of A by B into phi of C by D is equal to phi of A by B into C of D. Then lastly, phi of 1 by 1 is equal to 1 into 1 inverse, but 1 inverse is 1. So this is simply 1. So this phi is a isomorphism between frac D and some subfield of F. So what it actually means is that you have a field, you get a subring of that field. Subring not necessarily a it's not a subfield. It's only a subring of that field. Then you with that subring, which is actually an integral domain because any subring of a field is an integral domain. Um, so you can construct the fraction field using that subring. So this fraction field is constructed in an entirely different way. It is not related to that field. At least that's what you would think. But it so happens that that's not true. You end up with some subfield of the original field itself. That is, constructing this fraction field would so what what I can say is suppose you have this field um, just just an example. I mean not really an example, but I just to show what exactly we are doing. You had A B C D E F. Let's say you had something like this with one. So if this is simply an integral domain, right? Then we constructed the field by what procedure? How did we construct the fraction field? Well, I don't think you are understanding what a fraction field is. I think you forgot the definition. Let me remind you. Um, Frac D is the set of all elements A by B, where A and B are in D. I don't know why you are saying B has to be 1. I feel what is how do you construct frac D from D? If D was 1 A B C D, how do you construct frac D? What is frac D? Yes, that's the only frac D. There is no other frac D. No, no, that is, but that's not a field, right? That won't be a field. Yes, yes, that is only to show that in some form D is a subset of the field we constructed. That is, the set we started out with is a subset of the field we constructed. That's why we picked A by 1, B by 1, C by 1. To show that if you say frac D is a set of all A by B, then if you set B is equal to 1, you will get A by 1, B by 1, C by 1, etc., which is equal to the original set you started out with. So I start out with 1 A, B, C, D, E. Then I frac D is a set of all elements of the form A by B, C by D, B by E, etc. This will also contain elements of the form A by 1, B by 1, C by 1, etc. So these would be elements of D. But there are other elements also. So this is how you would do for a general integral domain. But suppose this integral domain that you picked was actually a subring of a field. And instead of constructing fractions like this, you could simply take this would simply also be equal to set of all elements of the form A B inverse, C D inverse, E F inverse, which will also contain 1 into 1, A into 1 inverse. This is nothing but A, B, C, etc. You can do this because B has an inverse if F it is a field. B has an inverse within the field. So this procedure, this field of fractions that you had constructed, we only did that because we didn't have inverses for each element in the ring, right? We said it is an integral domain, so all non-zero elements don't have an inverse. If all non-zero elements had an inverse, it would have been a field. Because of that, we couldn't do division, right? And we couldn't, because of that, we couldn't do A into B inverse. So we couldn't divide, in a sense, A by B. That's why we had to go in a roundabout manner by constructing fractions, by defining fractions themselves as A by B. And we had to define an addition and multiplication on that set. And we had to define the fractions as equivalence classes of a particular relation. But if you knew that the subring you had is actually part of a bigger field, and instead of constructing this fraction field in a roundabout way, you could simply take the inverse of each element in a field. You could take one element from the set Then you could take the inverse of every other element in the set in the field, and you multiply those two together. Then also you would get a field. Should I repeat that? Yeah. So when you start out with the integral domain, you don't have inverses for each element. That's why you have to construct this fraction set. But if you start out with a field, then restrict yourself to a smaller ring, which is an integral domain. Then there is a bigger field where you can get your inverses from. So you can simply construct a field containing that ring by taking all the uh, products of each of the element in the ring with inverses of elements also. So in that way, you can construct the field containing that ring. You don't have to bother with fractions anymore. Okay, that is the field of fraction. Uh, it's not that AB inverse won't belong to D. You are taking the bigger set containing all the elements of the form AB inverse. Yes. Uh, all the elements of D would belong to that set because you can always take A into 1 inverse because it's a subring, right? So 1 will be in the subring. Then you can take all the elements into 1 inverse, which would simply be the element itself. So every element of D can be written as in the form of AB inverse for some A and B. But there would be other elements also which would do not lie in this subring D. So it is kind of this, right? You kind of the way initially you had integers 1, 2, 3, 4, etc. Then with 0, then you found that this was not sufficient, so you added negative integers -1, -2, etc. Then you found that this is also not sufficient, so you took fractions half, 2 by 3, by 6, whatever it is. So you're kind of filling up the gap by taking more and more elements, right? The same way, suppose you had this field A, B, C, D. You had a lot of elements like this. Instead of this, let me write this. A field can, I'll show this later, but a field can be written as 0, 1, then alpha, alpha square up to alpha power q minus 2, where q is a prime power. Every field can be written, every finite field can be written in this way. 0, 1, and other powers of alpha. You can also write 1 as alpha power 0. So 0 and powers of alpha. This is possible to do for every finite field. Then suppose you pick some subring within this field. Let's say somehow alpha power 0, alpha power 1, alpha square was a subring of that field. Then what is the smallest field that would contain this subring? It might not necessarily be this whole field. It might be something smaller. So this is the subring, it's not a field, right? So some elements might not have inverse. So what you are trying to do is you are trying to first what you will do is you will try to include the inverse of alpha power 0 is alpha power 0. So then you will try to include alpha inverse and alpha square inverse to make it a field. So you try to include the inverses. But then closure also has to be satisfied. So you try to include alpha square into alpha inverse, alpha power 1 into alpha power minus 2, alpha power 0 into alpha power minus 2. So you try to include all elements of this form. And you keep doing this process. You take the product of all the elements. If you get a new element, you add it to this list. Then take the product of that element with everything else. If you get a new element, keep adding. Keep doing this until you don't get new elements anymore. Then at that point, it would be a field because every element you have already added inverses of each of these elements. So given a field, given a subring of a field, you can always add enough elements from the field to that subring to make it back into a field, right? At the end of the day, worst case scenario, you can simply add all the remaining elements of the field to that subring. Then that will give you the original field. But in a better scenario, you need not add all the elements of that field back. Maybe by adding a few elements, that will give you a field, a smaller field than the original field you started off with. Is that okay? Okay. In the next two classes, we will do finite fields. You are interested in finite fields or infinite fields? Okay. I will share it right now. Uh, you want field extension. What did you say? Could you repeat that? What you wanted? Uh, yes. I mean, extended field is simply, I mean, you have a field K and a field F, and K is a subset of F. Then you simply say K is a field extension of F. That's all. Field extension simply means that it is a larger field that contains the smaller field. Yes. Again, this it contained is actually in the isomorphic sense. It's not directly contained. The smallest field is might not be directly contained in the larger field, but there might be a smaller field within the larger field that is isomorphic to this F. So K is the largest field and F is the smaller field. There might be a subfield of K. Let's say it's called F prime, which is isomorphic to F. So in that sense, see, in abstract algebra, usually isomorphic structures are considered to be the same. So in that sense, F inverse and F are the same thing, just with different names for the elements. So in that sense, F would be contained in K. You would say uh, F is the base field and K is the extension field. And that is important only because In the finite case, not all, there's a definite relation between what can be a base field and what can be a field extension. Simply two different fields cannot be, simply any field cannot be a subfield of something else. There, it all depends on the number of elements. So just from the number of elements, you can tell whether one field is a subfield of another or not. Okay, I'll do finite field in the next two classes. That's bye.